Hello. In this video, I'm going to cover some of the issues involving or some of the calculations and considerations of entropy. In the previous video, we discussed this idea, this sort of statistical idea of what entropy is. It's a measure of the distribution of energy. And entropy has a lot about it in terms of determining the usefulness of energy. So if energy is highly ordered, for example, a battery has ordered energy, it can be very useful for doing work. But if energy is not ordered, then it tends to be less useful for doing work. So when an automobile engine burns fuel, some of that energy is used, transformed into heat, some of it's transformed into work. That heat can be useful, but once the heat is moves out into the environment, out into the air, it becomes less useful. And so one of the things we're going to look at here in this video is how we consider whether entropy is increasing for a process or whether it's decreasing for a process. And then once we do that, we'll look at a little calculation, simple standard state calculation you can do with entropy based on using table values. Okay, so let's begin by looking at a problem involving let's take a look, I'll bring this up. A problem involving changes of state and changing of conditions, physical conditions. So this problem is called predicting qualitative, right? So we're not calculating anything, we're just looking at qualitative differences. How entropy changes with temperature and volume. So this is specifically temperature and volume. For each system listed in the first column of the table below, decide if possible whether the change described in the second column will increase the entropy. Remember, the symbol for entropy is capital S of the system, decrease S, or leave S unchanged. If you don't have enough information to decide, check the not enough information button in the last column, okay? So let's take a look at the first one. The first one is a few moles of carbon dioxide, CO2 gas. So imagine you've got this collection of gas molecules. They're bouncing around in a container, okay? Here's the change. We compress, the carbon dioxide is compressed from a volume of 13.0 liters to a volume of 10.0 liters, while the temperature is held constant at negative 20.0 degrees Celsius. And in the third column, we want to determine whether delta S is positive, negative, or we can't tell. I guess the fourth option would be it's equal to 0, right? There's no change at all. So 4 options there. So notice the math symbols less than 0 means negative, right? Equals 0, we all know what that means. Greater than 0 means positive. So if entropy increases, the change in entropy is positive. If entropy decreases, in other words, if delta S is less than 0, that means it's gotten smaller. And then, of course, we have not enough information. So in general, here's what happens. As you heat a collection of gas molecules, they move faster on average. The distribution of speeds increases, but it also broadens. The possible velocities that can exist increases as you increase the temperature. They just move faster, so you have a broader distribution. Well, that broader distribution essentially increases entropy. And so if the temperature rises for a gas, in general, the entropy increases. The issue with volume is a similar one. The more possible positions that a gas molecule can occupy, the greater the entropy. Remember that previous calculation in the previous video where we said the entropy is k ln of W, where W is the number of positions. So as W increases, the entropy increases because there's just more available positions for the molecules. Same thing here. If the volume increases and there's more space available, that would increase the entropy. So the first one is compressing it. So the volume gets smaller. So if you compress it, there's fewer positions available. So the entropy should actually decrease. So your change would be negative. And then what happens to the temperature? Well, the temperature is held constant. So what they're saying there is the temperature is not changing. So that's not going to affect the entropy. So the only thing that would affect the entropy change here would just be the volume change. So if the volume gets smaller, that would be less entropy. Less entropy would be a delta S, which is negative, right? Something gets smaller, the change is negative. So that would be delta S is less than 0. Okay. Let's take a look at the second case. A few moles of of helium gas, helium, right? Noble gas. The helium is cooled from 52 degrees C to -5. So it got colder, right? In general, as molecules get colder, their motion slows down. So if their motion slows down, the distribution becomes more narrow. So they aren't as many moving really fast compared to really slow. They're moving closer in the same speed, closer to the same speed on average. So if you cool something, the entropy should decrease. But what does it say here? It says the volume's increasing. We're expanding the gas. So that's contradictory, right? If we're increasing the entropy if the volume goes up, but we're decreasing the entropy if the temperature goes down. So really you can't tell. You'd have to do a calculation on that, which we're not doing in this problem. So that's not enough information, right? If the two factors are going in the opposite direction, you can't really tell which one's going to dominate here. Ultimately, essentially what you would do is you would look to see how big was the temperature change and how big was the volume change. So if it was a bigger temperature change than it was a volume change, then the temperature would probably dominate that. But we're not going to worry about that for right now. We're just looking at qualitative changes. So if we have two contradictory, one goes higher, the other one goes lower, then we're going to say there's not enough information. Okay. Third one, a few grams of liquid acetone, which is CH32CO. The acetone evaporates, so it's going from a liquid to a gas. Evaporation means going liquid to gas at a constant temperature at 16 degrees C. So the temperature is not changing, so we don't have to worry about temperature. If something goes from a liquid to a gas, the volume is increasing dramatically, right? A little bit of liquid is a big volume of gas because the molecules are so widely spaced. So you're really expanding into a larger volume. Expanding into a larger volume means more positions available for the molecules. So that would be more entropy. So in this case, delta S would be greater than 0, right? Positive means greater than 0. We're looking at the changes. So the entropy in general, for the same material, the same temperature, the entropy of a gas is much greater than the entropy of a liquid. And in general, the entropy of a liquid at the same temperature is greater than the entropy of a solid. So solids have lower entropy, liquids sort of higher, not a dramatic amount higher, but higher. And then gases have a lot of entropy because they have a lot of available space to them. Okay. So this distribution of energy actually is connected to positions. Things can have different positions, they can have different energies. Okay, so there's that particular problem. Let's take a look at a second one. The second one is predicting qualitatively how entropy changes with increasing mixing and separation. Okay, so mixing, so think about it. If you're making a drink, you have some vodka and you have some lemon juice or lemonade or orange juice, I guess, right? You're mixing things together. So when things mix together, that jumbles them up, makes them less ordered. So that's an increase in entropy. When things separate, so for example, oil and vinegar, right? If you're making like a salad or water and oil, the water tends to go to the bottom and the oil, if it's less dense, goes to the top. The separation actually creates more order. So mixed is more disorder, more entropy. Separated is less disorder, less entropy. Okay. For each system listed in the first column of the table below, decide, if possible, whether the change described in the second column will increase the entropy S of the system, decrease S, or leave S unchanged. If you don't have enough information to decide, check the not enough information button in the last column. Okay, let's take a look at the first one. 300 milliliters of a solution made from sodium bromide dissolved in water. That's your system. So imagine, sodium bromide may not be something that you ingest, but you do ingest sodium chloride, right? So a similar kind of situation, it's dissolved in water. What are we going to do? We're going to crystallize 0.5 grams of sodium bromide. Crystallizes out of the solution without changing the temperature, right? So think about it. If it crystallizes, that means it's separating, right? If it's separating, you're going to get a pure crystal, and then you're going to have water, right? So it just turns out more mixing is more entropy, so less mixing is less entropy. So crystallizing a solid actually reduces the entropy. So reducing means a negative change, so that would be delta S is less than 0, okay? A mixture of carbon dioxide, which is CO2 gas, and oxygen, O2 gas, at 1 atmosphere and 26 degrees C. We're going to have an additional 2 liters of pure O2 gases added to the mixture with the pressure kept constant at 1 atmosphere. So notice, what are we doing? We're adding more material. We're mixing things together, right? If you're mixing things together, that's going to increase the entropy. So in general, also, more material has more entropy. So like if you have 0 material, if you have a perfect vacuum, you really don't have any entropy. You add matter to the universe, you now have entropy, right? So adding more oxygen adds more entropy. So delta S is greater than 0. That'd be positive value. A liter of seawater at 15 degrees C. Seawater is passed through a reverse osmosis filter, which separates it into 750 milliliters of pure water and 250 milliliters of brine, which is very salty water, okay? So think about it. What you're doing is you're taking a mixed solution, right? The water and the salt, right? Brine is very salty water. And you're separating. So now you have some pure water. Now you still have a mixture over here that's still has quite a bit of entropy. But again, separating things into pure substances decreases the entropy. Pure substances have less entropy than impure substances, if you want to put it that way. So that even though it's not completely separated, having that pure water is less entropy than having the mixture. So again, that would be a delta S that's less than 0 because that's a negative change. Something gets smaller, that's a negative change. So those are a couple qualitative problems. So let's take a look. There's another type of problem in here. Again, actually, this is, I think, a third type of qualitative, but this is looking at chemical reactions. So first one was volume temperature of a gas. Second one was mixtures and pure substances. This one right here is now looking at chemical reactions. It's kind of fun. These ones are, they're not that difficult. They're fun to, once you get the idea, they're pretty fun to do. Let's see. Sorry. Qualitatively predicting reaction entropy. Okay, so now we're looking at chemical equations. For each chemical reaction listed in the first column of the table below, predict the sign, which is either positive or negative, of the reaction entropy delta S reaction. Okay, so delta S reaction. So, I'll talk about this in a moment. If it's not possible to decide with the information given, check the not enough information button in the last column. So the format of these 3 questions is the same. Note for advanced students, assume the temperature remains constant and assume that all gases and solutions are ideal, okay? So no changes in temperature. Ideal means that they behave according to the ideal gas law if it's a gas or a gas mixture. Solutions have their own kind of dynamics of being ideal. But let's take a look. Here's the first one. Zinc, which is a solid. So think you got a mole of zinc, right? The coefficient is 1. So you have 1 mole of metallic zinc. Think of zinc as, what it is, right? Some metal, right? You got a little piece of metal here, big chunk of metal. So reacting with 2 moles of hydrochloric acid, which are dissolved in water. So that's a solution, right? So solutions in general have more entropy than pure substances. So zinc probably doesn't have that much entropy. Hydrochloric acid in water probably has quite a bit more, okay? got H plus, you got Cl minus, so you got two different types of particles, you got water, it's all mixed in, that's a lot of entropy. Maybe not as much entropy as gases, though. Gases have a lot of entropy. When that reaction occurs, you get a mole of zinc chloride aqueous. So again, you have these ions. Remember your solubility guidelines from Chem 11? This is a mole of zinc ions and 2 moles of chloride ions. When this molecule is formed, it's dissolved in water. You have a solution. And a mole of hydrogen gas. It's kind of interesting. So gases, as I said, tend to have a lot of entropy. So here's the way to analyze it. In general, solids have the lowest entropy, followed by liquids, followed by aqueous, followed by gases, meaning gases have the highest. Okay, so an aqueous solution has a lot, a gas has a lot, a solid has much less, and a liquid has much less. So essentially, you just compare the reactant to product side. On the reactant side, we have a solid, very little entropy, and 2 moles of an aqueous solution, which has a lot more. But on the product side, we also have an aqueous solution, which has a lot more. Okay, so in a sense, the HCl kind of cancels the ZnCl2 in terms of entropy, right? They're both aqueous solutions, so they are aqueous salts. So they kind of approximately cancel each other. HCl is an acid, not a salt, but it behaves in some ways like a salt, ions, right? So really what you do is you kind of compare the zinc to the hydrogen. The hydrogen gases have a lot of entropy. Zinc as a solid has very little. So that one, it probably looks like that's an increase in entropy because, again, the aqueous materials cancel, and then you've got a gas versus a solid. Gas has more. So the products have more entropy, so that's an increase in entropy. So delta S would probably be greater than 0. Okay, let's look at the second one. This one right here is ethene or ethylene, C2H4, which is a gas, so a gas, plus Br2, which is a gas, so another mole of gas, so 2 moles of gases. And then over here, look, we have a liquid, 1 mole of a liquid. Hey, gases converted into liquids. That's a decrease in entropy. Decrease in entropy, right? Because liquids have less. That would be a negative change. Decrease the entropy. That's negative. Third one, sulfuric acid. We have a mole of a liquid, forming an ion and forming another ion. Now that's a little tricky, but in general, if something becomes aqueous, it's now a mixture. If something is a liquid, it's a pure substance, right? When I say H2OL, I mean pure water. When I say H2SO4L, I mean pure liquid. So you have 2 liquids turning into 2 ions dissolved in water. That means it's more disorder because you have these ions dissolved in the water, right? So that's an increase in entropy. So delta S would be greater than 0. Okay, so again, solids, very little entropy, liquids more, aqueous more, gases more, in that order. Once you get up to the gases, you have quite a bit of entropy. Okay. Very good. One more type of problem in here, and that is actually now the calculation. The qualitative ones are interesting. I don't trust them in a sense. I like the calculation ones because we want to be sure about things. So let's take a look. So now this is kind of an interesting aspect of entropy, which is that we can do calculations with it. So let me bring this problem up. So calculating reaction entropy using the standard molar entropies of reactants. Using the thermodynamic information in the ALEKS data tab, calculate the standard reaction entropy of the following chemical reaction. MgCl2 solid plus H2O liquid forms MgO solid plus 2HCl gas. Okay. Round your answer to 0 decimal places. Okay, this is the first time I've seen a problem on ALEKS where it was 0 decimal places. Okay, so it says you can use the ALEKS data tab. Okay, so the values are in there. You just have to look up the standard entropy values. So before I do this problem, I'm going to go ahead and show you the equation we would use. So let me come over here. I'm going to write this equation down. Can we do it qualitatively? Can we make a prediction about whether the entropy change is positive, negative, or not sure? Hard to say. But if you look at it, it looks like we can, right? You know, if you think about it, you've got a solid here, you've got a solid there, pretty much cancel. They're not going to be equal to each other, but they'll cancel for the most part, not big difference between those two. But now you've got a liquid and a gas, right? Gases have a lot more than liquids. In fact, you got 2 moles of the gas, so that even doubles the amount. So that's going to be a positive change. Delta S will be greater than 0. We can do that. Okay, but having said that, what I want to do is I want to show you how to calculate it. So again, you're going to use the Alex data tab. For what are called standard entropy values. Okay. And here's the formula you use. Delta S, these are under standard conditions. Remember that little degree sign when we talked about enthalpy back in Chem 11? The degree sign means that this is being done under standard conditions, meaning generally 25 degrees C, although that's not explicitly part of standard conditions. Standard conditions are the material is in the state of matter that is standard at the given temperature that you're measuring at. Okay, so for example, oxygen gas is a gas at room temperature. So if we make a measurement at 25 degrees C and we're calculating the standard entropy change, we would have the oxygen be a gas, not a solid or a liquid. Likewise, aluminum is a solid at 25 degrees C. So we would have if the measurements are made at 25 degrees C and we're going to calculate standard entropies, we would use solid for the aluminum. Okay. State of matter does affect enthalpy, entropy, and what we'll see is free energy later on. Okay. Now, the delta S0 is typically in the units of joules, energy units, per Kelvin, temperature units, per mole. They're per mole, 1 mole. Okay. So what we do is we essentially look those values up. So I'm going to look them up here while I'm preparing this. And magnesium chloride is 89.6. Okay, so there's your value. H2O liquid is 7. I've seen it as 69.9, but in the Alex data tab, they have it as 70.0. That's perfectly fine. I've seen it as 69.96, maybe. That's what I'm thinking. MgO, solid is 27.0. And HCl as a gas is 186.9. Now, let me point out what I've been claiming throughout this whole discussion is that in terms of entropy values, gases are greater than liquids and liquids are greater than solids. Let's see if that's true. If you look here, we have a couple of solids. Well, the MgCl2 is actually greater than water, right? So it does, in fact, depend on the material. Magnesium chloride, even though it is a solid, has a little bit more entropy than the water does. Water is actually, as a liquid, has a very low entropy because of the hydrogen bonding that takes place in it. But they're close to each other, right? They're not big differences. But take a look at the magnesium oxide, MgO. That's also a solid. See how low that one is? So magnesium chloride actually has quite a bit of entropy because of its structure, and the magnesium oxide has a lot lower. So in general, those are all under 100. But look at the gas. See how much higher the gas is? HCl is a relatively simple molecule, but it has a pretty high entropy, 187 almost, right? So gases definitely have more. So that's the danger of doing these sort of qualitative assessments. comparing a gas to a liquid. Well, sometimes solids are a little bit more than a particular liquid. Water in particular is a low entropy. Other liquids tend to have greater entropies, but in general, if you were to do that comparison, we'll see what we come up with. Let's do the calculation. So the formula, so change in entropy for the reaction. I'm going to use the statistical symbol sigma, which means add up or sum, the summation of the products for the number of moles of the product in the chemical equation, that's the coefficient, times the standard entropy for that particular material. So this is products minus the sum of the reactants. So you're taking products minus reactants, just like we did with enthalpy changes. Put an R there and then times S naught. So just so you know, the S that we're referring to, so there's your S values. Oops, sorry, I got it reversed. My apologies. Sometimes I can't think backwards. It's products minus reactants. So the S that we're referring to, it's referring to the values in the table. So each of those refer to the values in the table. N sub R and N sub P are the coefficients in the balanced equation. And then there's a 2 to the right. So you're using those ones right there. So let's go through and calculate it. Okay. So remember, it's products minus reactants. So the first product is MgO. And the coefficient is a 1. So what you do is you say 1 times, and you look up your MgO, 27.0. I'm not going to put the units in because it just takes up a lot of space. And then you do the second product. So a 2, right? There's a 2 in front of it. And then HCl is 186.9. Okay. So now I'll put those in parentheses and brackets in any case, just so that we're talking about how this is the first term. And then we're going to subtract the second term. So minus the first reactant is 1 is the coefficient and 89.6 plus second reactant is water, so 1 times 70.0. Okay, so see how I put those all in the brackets just to do products minus reactants. Okay, and I'm just going to bring up my little calculator here. Okay, so we have 1 times 27.0 is just 27.0, of course, plus 2 times 186.9. So I get, oh, I'm sorry. Every time I use a different calculator, you have to get, you just have to get used to the notation that you have to use with it. Yeah, 400.8. So entropy values will always be positive, but the change in entropy could be negative. Okay, so we have that. I'll put it in brackets just so you can see what we've done. Minus, let me clear this. So we have 89.6 plus 70.0, because it's 1 times 70.0. 159. Get that right? Oh, I'm sorry. That was the, oh, okay. No, that's right. 159.6. Okay, let me just make sure I got these values right here. So MgO is 27 and HCl was 186.9. Okay. So those are your products minus 89 and 70. Okay, good. So now let's take the difference between them. Sorry, I'm going slow on this, but I just want to make sure I get it right. 159.6, 241.2. So notice it is positive, so I'll explicitly put a positive there. 241.2, just so it's clear. minus a positive. Okay. So there's your delta S, right? Now, again, the units are joules per kmol. So there's our delta S. Now, did it increase or did it decrease? That's an increase, right? Because delta S is greater than 0. So that's an increase in entropy. Okay. So the calculation seems to line up with our prediction, right? That forming the gas molecules is going to increase the entropy. So notice the reason this ended up positive is because we had this right here, 2 moles of a gas, right? So that was like almost 400 right there. In fact, it looks like this entropy change just forming the gas molecules, the 2 moles of HCl, that was actually a greater amount of entropy than both of the reactants together, okay? So yeah, forming a gas really does tend to increase the entropy. So this process would result in more disorder, which in a sense means less useful energy. Once this is done, the entropy results, the change in entropy results in a less useful form of energy. Okay. I'm thinking I'll do one more. Okay. So let's bring up one more. Calculating the reaction enthalpy and entropy, not enthalpy. Using the thermodynamic information in the Alex data tab, calculate the standard reaction entropy of the following chemical reaction. And then here's our equation, right? The balanced equation. Okay. So 2 moles of ammonia, NH3 gas, form 1 mole of N2H4 gas plus 1 mole of H2 gas. So that's a little tricky. It's not obvious to me whether that's going to be positive or negative change, because we have 2 moles of a gas on the reactant side and we have 2 moles of gas on the product side. My guess would be it would be an increase in entropy because 2 different materials, you know what I mean? If you have a pure substance, generally pure substances have less entropy than mixtures. So it may very well be that by having 2 different materials on the product side, that results in more entropy. And so going from less to more is a positive change. So my guess would be an increase, but let's find out, okay? Let's take a look. So 2 moles of ammonia forms 1 mole of N2H4, which is, I guess that's hydrazine and hydrogen gas. Interesting. So I guess that's a way to form hydrazine, which is a rocket fuel. It's a very energetic material. Okay. So what I'm going to do is look up the values for each of these. So ammonia as a gas. So there's our entropy. Remember, these are standard conditions. So ammonia is 192.8. And then hydrazine, 238.5. And then hydrogen is 130. So, okay. So again, your change in entropy under standard conditions is the sum of the products of the number of moles of the product times the standard entropy of each material minus the sum of the reactants of the number of moles of each reactant times the entropy, the standard entropy. Okay, so let's figure this out. Let's do products. So the products are N2, it's a 1 and that's a 1, right? So 1 times N2H4 is 238.5. 1 times 130.7. So there's your products. Minus your reactants, right? So I did products, and I'm doing reactants. So the reactant is 2 moles of ammonia, which is 192.8. Okay. So let's take a look and see. That's, it's not a real complicated calculation, but you do need to do it. So 238.5 plus 130.7 is 369. So remember, you're going to get positive values for these calculations until you take the difference. Then you could get a negative. A negative just means that it decreased. And then 2 times 192.8. That's 385. Okay. So now it looks like it's actually going to be negative, right? It's going to be a decrease in entropy, not by a whole lot, though. They're pretty close to each other. So 369.2 minus 385.6 equals, and you get negative 16.4. It's a very small difference. We would almost say the change in entropy is close to 0. It's a tiny difference. Again, the units are joules per Kelvin, but it shows the limits of our sort of qualitative analysis of a gas or a mixture. It turns out that actually forming this mixture, 1 mole of N2H4 and 1 mole of H2, it actually has a little bit less entropy than 2 moles of ammonia. Okay, so be careful with the qualitative. That's why they make the qualitative questions so kind of dramatic differences, a mole of a solid going to a mole of gas, that sort of thing. Okay, so there's our little kind of intro into entropy. The next issue that we're going to deal with in the next video has to do with how we relate entropy changes for entire processes. So what we've just covered is what we would call the change in entropy for a system. So what we're going to do is we're going to start doing entropy changes for surroundings as well. And then we'll look at what's called the second law of thermodynamics. So that will be in the next video. Okay, take care.